We're going to talk about media, but from the perspective of media design. And this first slide is a list of the important things that bioretention media needs to do for us. First, one of the important things is high enough infiltration rates, surface water drawdown, and system dewatering. That's all part of your modeling procedure that you incorporate in your design. Infiltration rates that are not too high so that you get adequate pollutant capture. And that makes a difference. The residence time of that water in the media makes a difference as far as how well it performs. Although, I will say this, a lot of the media we're working with now is high flow media, 50, 100 inches per hour, and we're still seeing very good treatment. Nevertheless, there is a maximum infiltration rate that is now prescribed in the Stormwater Management Manual, and we'll talk about that. You need to support plants, healthy soil for those plants, and water quality treatment. This one kind of added recently, you need to balance the nutrient availability for growing plants and retention, nutrient availability and retention, and copper retention at very low effluent concentration. So we have, some of our targets are quite restrictive. For example, industrial stormwater permit, industrial permittees are looking at 14 parts per billion of copper for their benchmark. To do that consistently, that's challenging. And so how do you balance the needs of the plants for nutrients and the media that you might be using, but have these low effluent levels? And that's very challenging. So these are the kind of the big picture items. A little history. Typical, what we've seen across the country over the years, some places still using this, topsoil, some sand, and some leaf mulch, maybe compost. We probably use more compost in bioretention media than anywhere else in the country. I'm guessing. I'm not positive about that, but it's likely. A lot of other parts of the country will use, for example, a leaf mulch in their media. That's something that's been used in the past quite often, still today. There's issues with this guideline. We started thinking about these issues long ago, over 10 years ago. Topsoil can have a lot of fines in it, and fines are the particle size, mineral particle size passing the 200 sieve. So that's small. That significantly affects your infiltration rates. Topsoil can be well above that. Minimum organic matter content, 10% by dry weight. That's an old recommendation. It's hard to control that with topsoil. You just don't know what that organic matter content is going to be. Material control is huge. Topsoil, we have no guidelines really, rigorous guidelines for topsoil. So you could get topsoil from Bob's backyard one day and Jack's construction site the next, and unless you have a supplier that you know really well, and you're going to get sandy loam or loamy sand and consistently get that, which is rare. That's very rare. It's very challenging to have any consistency. So material control is a big one. There's also been contaminant flushing observed from topsoil blends as well, and the agricultural literature is replete with research showing nutrients, materials being released from agricultural soils when you plow them, when you disturb those soils, right? And that's what we're doing with bioretention media, right? We're mixing it all up, throwing it in a hole, and then expect it to perform immediately. So there's a bunch of issues with the media guidelines and the materials we're using. That led to, back in '09, this project to try to come up with some different materials that we had more control over. You could have confidence that there's consistency in those materials. All over Western Washington here looked at different sand suppliers, and we found some material that we currently prescribe today. It's called a utility sand or a dirty sand. It's very similar to a C33 sands that are byproducts of the cement industry. But we found some of these dirty sands, utility sands, that seemed to work quite well. They had just under 5% fines, passing the 200 sieve. And some of the gradations seemed to work really well. And so we started gathering those up and testing them. And what we found was, on some of our testing of these sands, was looking at the hydraulic conductivity. So to put it in simple terms, that is just the movement of water through a column of the sand, and percent fines. And you can see in this on this graph here that we found a very strong relationship between percent fines and hydraulic conductivity, a very strong relationship. Well, the soil scientists have known this for decades. No harm in going back and reconfirming, and this helped us as far as narrowing down and understanding the materials that we were working with. So we're starting to think, oh, well, maybe we could prescribe some of these sands that would work well. Well, sand alone will grow plants. And then we started to think, oh, well, we're going to have to put something else in there. How about some compost? Let's put some compost in there for water holding capacity and grow plants and all that. So that's sort of how this whole thing started and how we got to our 60-40 prescription today. Another thing we discovered about the sands was that the particle size distribution is also very important. This is some research that we did years ago looking at the particle size distribution and how that affects hydraulic conductivity. Same thing here on the vertical axis, hydraulic conductivity, that's KSAT, saturated hydraulic conductivity. And then this coefficient of uniformity. And that's just a measure of the particle size distribution. So that's coefficient of uniformity is the ratio of the sieve size that passes 60% of the material in relation to sieve size that passes 10% of the material. It's just a way of understanding the different particle sizes in sand. And it makes a big difference as far as how well it drains. And what we found was there is a certain coefficient of uniformity that's recommended that gets you in the ballpark as far as permeability for your media. So this is a little bit of background on where we are today with media. And I'm telling you this because there's just a lot of confusion and there's a lot of research going on and there's a lot of change. So I think it's helpful to understand where we are, where we've been, where we are, and where we're going. So we're gonna now talk about the default media and what you get when you use the default media. You can use the default media, 60% sand, 40% compost. Comes with all these prescriptions. Or you can design your own. In the past, what we've seen is that some of the landscape architects have been hesitant about the 60-40 mix. It's not going to grow plants. Well, we know that's not the case now. Stuff grows plants amazingly well. But there's been cases where landscape architects and other plant people say, no, I'd really like to design our own mix because I think the plants will grow better and all that. So there is a pathway. You can do that if you want. So it used to be that if you use the default 60-40 mix, you use 6 inches per hour as your infiltration rate. It just recently changed. We successfully lobbied ecology to change it. This is still part of the kind of guidelines, 18-inch minimum soil depth for enhanced treatment. So if you use a media depth of 18 inches, you get to claim enhanced treatment. And that's significant as far as your treatment goals. So that has to do with metals, phosphorus, and hydrocarbons very loosely. At any rate, it has to do with metals and hydrocarbons, phosphorus. And so if you use 18 inches of the 60-40 mix, you get to claim enhanced treatment. And we've seen from some of the data that maybe is a little dicey. So these are some of the guidelines that come along with the default mix, and we're going to talk more about that. Here's the particle size distribution for the default sand. It's in the manuals. And we found that this distribution, particle size distribution, and a coefficient of uniformity of at least 4, and the mineral fines at about 2 to 4%, less than 5, gets you in a pretty solid ballpark as far as the permeability. It varies, but it's reasonably close. That's just a little bit on the default mix. It's in the manuals. And I should mention, actually going back here, this 6 inches per hour has changed to 12. So we just recently kind of assembled the research and data out there on the measurements we've done in this region on bioretention media and found that the infiltration rates can be quite high, 30, 40, 50, 60 inches per hour, and that in reality, for the default blend, it should be more than 6 inches, and we were able to push it up to 12. If you're not going to use the default mix, and we're seeing less of this, but it's still out there, and so it's worth to go over this. So if you're not using the 60-40 mix, you want to define build your own, there are some guidelines. The long-term infiltration rate for sizing and flow control capacity, a minimum of 1 inch per hour. That should be really easy. If you can't do that, you maybe ought to rethink your media. There's a set of tests that we recommend. Again, this is all spelled out in the manuals. There's a lab test, ASTM D2434 and ASTM D1557. 2434 is the actual hydraulic connectivity. You put the stuff in a cylinder at a very specific way and you measure infiltration. The 1557 is a relationship of density to moisture. And so you go through these different tests. The lab does that for you. It has to be a minimum of saturated hydraulic connectivity of 1 inch per hour. So the lab takes care of that. Now you're designing. You've built your media and you're going to design your bioretention. And now there's actually now correction factors for the media. So I want to be real clear here. We talked about correction factors for the subgrade, right? What were some of the guidelines? Site variability, the test you use, right? Correct, and there are correction factors that go with that for the subgrade. Now we're talking about different correction factors. We're talking about correction factors for the media. So anybody remember what the correction factor is for sedimentation, fouling of the subgrade for bioretention? It's a round, very round, simple number. 1, that's right, 1. Because the media provides a great filter before any of that sediment would get to the subgrade. Okay, so that's the subgrade. Now we're talking about the media. Well, there is sediment coming into the media, and it's filtering that sediment. So if your contributing area is less than 5,000 square feet of pollution generating surface, PGS, less than 10,000 square feet, what's TIA? Total impervious area, and less than 3/4 acre landscaping, you can use a correction factor of 2. So what is 2? If you use a correction factor of 2 and you have an infiltration rate of 10 inches per hour, what would your design infiltration rate be? Correction factor is 2. Your initial measured rate is 10 inches for the media. You apply a correction factor of 2, what's your design rate? 20 or 5? 5, that's right. It's a little confusing. You know, it seems like, oh, 2, why shouldn't it be 0.5? That maybe, maybe that would be a little bit more rational. But at any rate, that's how it's done. If you're over those thresholds, you have to use a correction factor of 4. So this really pushes you to design for small contributing areas, right? The difference between 2 and 4 is a pretty big deal. And this has to do with the thinking that the larger the contributing area, the more sediment, the more junk that's going to be coming into that bioretention area and potentially clogging that media. All right? So these are for the media, not the subgrade. Different. 2 different. So now when you're designing correction factors, you're thinking about 2 different areas. Subgrade, media. Again, if you're not using the default media, there's also sizing for water quality treatment or infiltration rate guideline. It used to be 2.4 inches per hour. That's an old guideline. And we have spent the past decade or more unraveling where some of this stuff comes from. We still don't know where 2.4 ever came from. And we think it came from, kind of a loamy topsoil. We think it drained, that's a kind of a typical infiltration rate. And it's hard to track this stuff down because some of it was in, the back room somewhere. And I was like, oh yeah, that sounds like it'll work. As we've talked about, the research indicates that higher infiltration rates provide performance necessary to meet this enhanced treatment when you're using 18 inches of this stuff. As we talked about, Ecology now accepts 12 inches per hour for the high end. So 1 inch per hour minimum, 12 inches per hour maximum. Those are the infiltration rates that you use when you're designing your own media. There's other criteria though. There's the infiltration rates, but there also is organic matter content. Should be within the range of 5 to 8% by weight. CEC, but you know what that is? That's right, cation exchange capacity, 5 milliequivalents per 100 grams dry soil, and 2 to 5% mineral fines. So that's the guidelines for developing your own media. And lots of people are using the default mix, but there's still folks designing their own. So we've actually talked about all this, all the updates and all that. I'm gonna go ahead and kind of just run through these really quick. The compost sand mixes, excellent water quality performance for zinc, hydrocarbons, and bacteria. You really need to design with caution. if you're concerned about phosphorus, nitrogen, and copper, I would add here. And there are memos out now from ecology restricting where you can use that 60-40 mix. So you just need to be aware of that. The 2 to 4% passing the 200 sieve is ideal. This is the hardest thing for the aggregate suppliers, and if you're designing your own mix, this is the most difficult thing you probably have to deal with. It's tough to get it in that's a pretty tight range. But it's doable, and it's being done. Up to about 10 years ago, the aggregate suppliers, the language was, that's impossible, we can't do it. And I found out that the translation was, we don't see a market, so we're not willing to do it. And now there's a market, and voila, we have it. So it's, you know, that was interesting to learn that language. Coefficient uniformity is important, but not a strict criteria. But the particle size distribution is important as far as how this stuff drains. And small variations in these things make a big difference. Really changes how the system behaves, or the media behaves. If you're going to use topsoil, and this is really going away, I don't know if anyone is using topsoil still in Western Washington. If it is happening, it's very few. If you are going to do that, and you won't be doing this for bioretention areas, that's not going to fit the current prescriptions. For a rain garden, yes, right? But for bioretention, you're going to be, doing a more designed media. But in the cases where it might be used, you need to monitor that very carefully if you're using it. If you're using these sandy soil media, which most people are now, the sand and compost, they're very well drained. So you have to be careful about your plant selection. So we've had numerous cases where using these sand and compost mixes, it drains quite rapidly, put in plants and they die because the system is draining so rapidly. So you just have to work with your plant folks carefully on the right selection. We have done 3 different university programs have now confirmed that you can use a saturated zone for nitrate removal. Remember, we've talked about the flushing of nitrogen, phosphorus, and copper. Nitrogen, we found that you can successfully remove nitrate by using a saturated zone. How do you create a saturated zone in the bottom of a bioretention area? Elevated underdrain, and there's a number of different designs, and we talked about some of those. You simply create an elevated underdrain, so you have a saturated zone underneath. That saturated zone promotes bacteria within that saturated zone to use the nitrogen for the respiration process. So it converts nitrate to nitrogen gas. Nitrogen gas is given off, and it will speed up global warming and climate change dramatically. No, I'm just kidding. I don't know how much nitrogen comes out of bioretention areas, but at any rate, you convert nitrate to nitrogen gas and can significantly reduce nitrogen levels. That's good news. We still need more work on the copper capture, but we've got some materials that are working pretty well. I don't know why that's out of order. Again, phosphorus is really unresolved. It's the toughest problem we face with bioretention right now. And just to by way of context, we have guidelines for compost. We actually have quite restrictive guidelines for making compost in Western Washington. And under these WAC guidelines, there's things like organic matter content, metals, debris, garbage, plastics, those sorts of things that could be in that stuff. And there's a whole list of criteria for compost suppliers and how they make compost. And we've put those guidelines in, for example, the LID Technical Guidance Manual, as far as guidelines you need for your compost. Well, as it turns out, those compost guidelines are not meaningful for compost in a stormwater filter. They're great for compost for your garden, but for a stormwater filter, we are in the process now of really completely rethinking the guidelines for organic material that goes into a stormwater filter. So, when you see, just realize that those WAC guidelines that you're going to see in the manuals are not really applicable for organic material and compost in stormwater filters. And we're working on changing that.